Hello students, today we're going to be taking a look at section 1-3, solving equations. So verbal expressions and algebraic expressions. We're going to be taking a look at a chart and it will suggest some ways to help you translate word expressions into algebraic expressions. Any letter can be used to represent a number that is not known, as you know, in pretty much every algebraic expression you've dealt with. So let's take a look. Word expressions: and, plus, sum, increased by, more than, this would be the operation of addition. Minus, difference, decreased by, less than is subtraction. Times, product of, as in half of a number, would be multiplication. And then lastly, divided by, quotient, for example, is division. So let's take a look. Example 1, write an algebraic expression to represent 18 less than the quotient of a number and 3. So 18 less than the quotient, that's going to be indicative of a subtraction of 18. But what? From the quotient, they say, so the division of a number n they use for the variable, and 3. So n divided by 3 would be that representative expression. N over 3 minus 18 is precisely what you need to write for this particular algebraic expression. Example 2. Write a verbal sentence to represent 6 times the quantity n minus 2 equals 14. You do need to be very careful. For example, comparing this problem to 6n minus 2 as opposed to 6 times the quantity n minus 2. It is a different expression, therefore a different verbal sentence, and vice versa. If you were given a verbal sentence and had to write it algebraically, just be mindful of what the language dictates as you continue. So 6 times the difference of a number and 2. So I actually put parentheses around difference of a number and 2 just to kind of designate that you are multiplying by the difference. Okay, so then of course set it equal to, or say is equal to 14, and that puts a nice finishing touch on this particular verbal sentence. Be careful because we will run into this possibly later here. Exercises. So I've done a variety of problems here. Typically the ones that I've written in blue or in a different color, typically that's when I do it as a class. So these might be questions, for example, that maybe you try on your own if we don't happen to get to all of them, and then cross-reference, go back and see how you should have done. Let's just jump in. Write an algebraic expression to represent each verbal expression. So number 1, the sum of 6 times a number and 25. So the sum again means plus or add. 6 times a number, I chose x, and then what? 6 times a number and 25 are being added. So as you can see, 6x plus 25. Number 2, 4 times the sum of a number and 3. This actually relates nicely to example 2 from up above. So 4 quantity x plus 3. Be careful. If you don't put the parentheses in there, you're technically not speaking to 4 times the sum as a separate entity. Please note, you got to differentiate. So 4 and then parentheses x plus 3. It's a big difference. As you see here in the next problem, 7 less than 15 times a number. So there's 7 less, so you subtract 7 from 15x. Notice again there are no parentheses, because if there were parentheses, then you're actually speaking to 15 times the difference of a number and 7, and that's not what is happening here. Unlike, again, the prior problem, number 2. Let's take a look at some of these problems in blue, and then I'll maybe have you try some on your own if we don't finish. I'm going to stick to mostly doing the problems in red. But again, if we do a couple problems in blue here and there, that's okay too. So it says for number 4, the difference of 9 times a number and the quotient of 6 and the same number. Okay, so difference again, that means subtraction, of 9 times a number. So 9 times a number, that's easy, 9n I would argue. And so we're taking the difference of this first expression or term even, and the quotient. So quotient meaning division of what? 6 in the numerator and the exact same number n. So it makes sense that 9n minus 6 over n works in this context. I would like you to try 5 and 6 on your own and cross-reference, compare what you get to these two answers separately. I'm going to move on to number 7. 4 times the square of a number increased by 5 times the same number. So when we talk about the square of a number, you're going to have to use an expression to the second power. It's 4 times the square of a number, so 4 times, you don't see the times symbol, but it's 4n and then the quantity squared. Increased by, that means you're adding, and then what? 5 times, so 5 and then the same number n, so 4n squared plus 5n. Next, write a verbal sentence to represent each equation. Number 9, 3n minus 35 equals 79. So what I noted here, I said 3 times a number minus 35, and then I just simply wrote is 79. And this is exactly a good version that would be acceptable. There are other versions that I'll accept. Instead of, let's say, minus, you could use the word difference. Instead of is, you could actually add is equal to. That kind of thing is totally okay. So please make a note. You might want to cross-reference not just my answers here, but also the answer keys. As I noted in the past, right here as a section all the way down at the bottom in your content library. I'll have you try number 11 later on your own. Let's move on. So moving on, you can see here we're talking about properties of equality. To solve equations, we can use properties of equality. There's addition and subtraction properties of equality, such that adding a plus c, it equals b plus c, and a minus c equals b minus c. Quite simply, adding c to the same side, or to both sides of the equation, or subtracting c from both sides. If in fact a equaled b in the first place, it's a true statement. It's basically balancing an equation if you think about it. Multiplication and division properties of equality work in the same basic way. If a already equals b for any real numbers a, b, and c, which is also true in the last property, of course, multiplying both sides by c or dividing both sides by c holds true. Example 1. So basic balancing. Solve 10 minus 8x equals 50. So the first step, the original equation as you see, but go ahead and see that subtracting 10 from both sides. On the left it cancels, but on the right simply 50 minus 10, of course 40. Dividing then by what? Negative 8 to get the variable by itself, and therefore x equals negative 5. You could actually plug this into the original problem and it will in fact equal 50. Example 2. This is a first example of which you're solving an equation for y. You're not actually going to get a number here. Another depiction or another way to frame this is something called a literal equation. It's also just using an expression to solve for another expression basically, or a variable in terms of another solved for. So in this case 4x plus 5y equals 100, and you're going to solve for y. So because we want to get y by itself, subtracting 4x makes perfect sense. So if you do that, these cancel. Therefore 5y equals 100 minus 4x. Again, trying to get y by itself, I would argue is pretty nice and easy if you simply divide both sides by 5. Remember to divide everything by 5. In doing so, you'll have y here, 100 fifths, or if you write it as an expression in parentheses, actually their notation is just as good, writing it as 1/5 times the quantity. Then distributing, again, 100 fifths is going to lend itself to 20 anyways, and negative 4/5 x as a full final expression. You see y equals 20 minus 4/5 x. You'll be doing quite a lot of this when it comes to working with linear equations down the road. So let's take a look. Got a few to take a look at, maybe in red, and I'll maybe have you guys do some in blue on your own again. So solve each equation, check your solution. The checking part I'll leave up to you. Quite literally, that is taking your final answer and plugging it in to see if it's true. Number 1, 3s equals 45. Quick and easy. Divide both sides by 3. 45 thirds, of course, 15. Plug it in. Does it work? It should. S equals 15. Number 2, we're trying to solve for a, so subtract 9. 17 minus 9, so 8. divide both sides by -1, of course, then a equals -8. Plug it in and it works. Number 3. This particular equation, 5t minus 1 equals 6t minus 5. You can subtract 5t from both sides, and I also added 5 at the same time. So 5 minus 1, that's 4, 6t minus 5t, that's t, and you end up with 4 as t. Pretty straightforward, I would argue. Please try those next 3 questions in blue on your own and cross-reference my answers, and of course the steps. As I move on, we're going to go ahead and take a look, and don't mind this right here. That will be something we don't do necessarily. You'll see your homework later on the calendar. So I'll quickly delete that. But we're going to go ahead and take a look at solving an equation or formula. It's also called a literal equation, as I described earlier, for the specified variable. So to kind of take a quick look here at one that's already done for us. And I will probably pick one that is already in blue, let's just say. I can see number 19. We've got 3 pq over r equals 12, and you want to solve for p. So right now as it stands, p is already in the numerator. So all you need to do is, well, you can either divide by 3 and multiply by r, or you can take the reciprocal. In other words, multiply both sides by r over 3. And as it turns out, q can also be written in that particular fraction, which I show right here. So r over 3q is the reciprocal of 3q over r. So if you do that, if you multiply both sides by r, so you have 12r as you see here, and then 3q on the other side, of course, again, you got to do it to both sides. It's in the denominator, so it would be 12r and then over 3q. You can simplify 12/3, of course, as 4. So 4r over q would be a good final answer for that particular question. Number 20. We've got here 2xy equals x plus 7 and solve for x. If I'm going to get x by itself here, and because as you can see there's x in 2 different expressions, it makes sense to first get x on the same side. So I subtracted x. So what you have in this next step, as you can see, is 2xy minus x equals 7. So you may be wondering still, well, if x is in 2 different spots, how am I going to get it such that it's x all by itself on one side? So there is a clever little trick here that you may recall from Algebra 1, and that is if something occurs in more than one term, you can factor it out. It's called a GCF, or greatest common factor. So I'm going to go ahead and show my next step here. So if you factor out an x out of both of these, there it is. In parentheses, you'll have 2y, because that's what's left after you divide out the x. And then out of here, you'll be left with just minus 1. If you want to double check, distribute the x, and sure, x times 2y is 2xy. X times -1 is -x. And of course, that still equals 7. Next step, and really the last step, is to divide both sides by the whole quantity. Be careful, the whole deal, 2y minus 1 has to be divided. Do it to both sides, so 7 over parentheses 2y minus 1. Final answer, there it is. X equals 7 over the quantity 2y minus 1. I do encourage you to take a look at some of those other questions there. 17 I skipped. Please take a look at that off to the side. That is a question that you can see off to the side. Even some examples there at the bottom that might benefit you in the long run. So take a look at those. But before we end today, I do want to make a note of number 24 because it just may be the hardest one. On 24, getting m by itself is similar to 20. So I went ahead and I factored out the GCF of m. Notice what is left. Not a very nice looking expression. However, if you divide that whole thing by that quantity, again 20 divided by that, I have this kind of messy looking fraction still, so I got a common denominator of n, multiply the second part there, 5 by n over n, to show or get that common denominator. Simplify to the next step, multiplied by the reciprocal, and the final answer, this is the best answer, is as such. Please take a look at all the other problems there that I haven't yet done and check your answers.